All right, so now we're going to take it up a notch, and it's not even really that much more difficult, but we're going to talk about continuous distributions. So before we were talking about like a discrete mass, like one point mass kind of situation. So now we're going to take it up a notch and talk about continuous distributions. But just to reiterate, if you want to find the moment of inertia for a discrete bundle, you just sum up all the different moment of inertia contributions. So we did a couple examples with that, and you might have guessed it. That's sigma, which is kind of discrete, like add up like that. We're just going to turn those into an integral right here. Okay, so still have the r squared, Instead of m, it's going to become dm, and that's for a continuous distribution right there. I'm forgetting to dot my i's. I crossed my t's though, so that's good. So one little thing, sometimes on the AP physics test, this is one of the tougher questions, and people get a little flustered, but sometimes they'll even give you a point just for recognizing, oh, I'm in a discrete situation. I wrote down the formula for a discrete moment of inertia calculation. They might give you a point for that. And sometimes on the AP test, if you have like a rod or like a pole of length, whatever, and we'll do some examples here, and you want to do a continuous distribution like that, you want to do a continuous question like that, if you realize, hey, I'm going to use the integral instead of the summation right there, then this right here, they might even give you a point for doing like, oh, that's the integral from 0 to m of r squared dm. So just make sure you don't jump steps. You just don't freak out. It's going to be a tougher question, but sometimes you can really rack up the points in those tougher questions. All right, so here's the question here. Example 1, find the moment of inertia for this. Find I for this. It's bad grammar, but find the moment of inertia for this uniform board with a point of rotation at the left endpoint. Because remember, it's moment of inertia depends on the mass of your system, but it also depends on where the point of rotation is because that affects your R value. Okay, so I'll show you the situation here. Kind of like the top view of a door, you have a hinge and then you have like the length of the door, but you have some kind of point of rotation. I marked it with a little red star right there. And so that's your point of rotation. And then you have the length, which is relative to that point of rotation. That's your 0 point. That's very important to know, is that wherever your point of rotation is, that's your 0 point for the problem you're doing. Okay, because you can picture like if that was my point of rotation and this is my length right here, that's a vastly different situation than if my point of rotation, like a revolving door, were right here. And so in that case, the 0 point would be right there. We'll talk about that in our example 2. So I know that's the formula for moment of inertia. You integrate over m, right? But a lot of times it's easier and makes a lot more sense to integrate over r because our bounds of integration can really tell us a lot about our situation. So instead of integrating over mass, we're going to do a little switcheroo step and we're going to integrate. And if you take college physics, they're not going to call it the switcheroo step. Instead of integrating over the mass, we're actually going to integrate over the r, and I'll show you what that means here in a second. Here's our formula. But instead of integrating from 0 to m r squared dm, we're going to do this little switcheroo step, okay? And once we do it, it'll make sense, but you might just have to follow along for a second. So that's the definition of moment of inertia. But one little thing, we're going to say it's a uniform rod, which means, you know, the mass per unit length is constant throughout the board. If you took this mass divided by this length, it'd be the same as you took the whole mass divided by the whole length. So it's not like thicker in some parts or more dense in some parts. It's got a linear mass density that is uniform. And we'll do an example. It was a AP FRQ from about 3 years ago, 2018, where it's a non-uniform board. And that's a release question. You can check it out if you Google it there. But we're going to talk about a uniform board. And this is called linear mass density. And the Greek symbol lambda, Lambda, is what they use to represent it. It's how much mass per unit length. And we're going to say our lambda is constant throughout this board. So mass per unit length, it's just some kind of nice uniform value. And you're like, well, why do I care about this? Just hang on and you'll see where we're going. So our goal is to take it from, instead of integrating over mass, I'm going to do a little switcheroo step here, and we're going to integrate over the length of the board. And that's what we're going to do right now. So lambda, that's the Greek letter, it represents linear mass density. And that's just fancy talk for how much mass is there per unit length. And you can picture, like, is it a very dense board, lots of mass per unit length? And in our situation, since it's a uniform board, we're just going to say it's got some total mass, some total length right there. Okay? And I'm just going to rearrange it. I'm just going to put the L over to the other side. So if you ever look at this, if you take lambda, which is mass per length, times the length, that makes sense, it equals mass. Okay? So this is the switcheroo step. Instead of integrating over mass, I'm going to do this little trick right here, and we're eventually going to integrate over the length of the board. Okay? So one little thing, when we integrate, we're not necessarily talking about the total L or the total M. We're going to start from here. We're going to integrate this little slice plus this little slice plus this little differential slice. And so we're going to integrate all those differential slices. So instead of just calling it L, we're going to integrate dr. So some little differential length right there. And I called it R just because technically L is a constant because that's the whole length of the board. So I'm just going to say some little differential R, and we're going to say, hey, you know what? If you take that little differential R times the linear mass density, that'll give you some little differential M. And if you want to prove this to yourself, The label for, length or radius, whatever you want to call it, is meters. And we know linear mass density is a kilogram per meter. So if you ever take a kilogram per meter times a meter, whoosh, you'll be left in kilograms. So all we're doing, we're doing a little switcheroo here. Instead of integrating over mass, we're going to integrate from some point 0 right here, our point of rotation, out to the end of the board length L right there. And we're just going to sum up the contribution of this slice plus that slice plus that slice plus that slice. And we're going to put our bounds of integration from 0 to L. So we're just doing a little switcheroo step. And you might be like, oh, why do we care that the differential mass dm equals lambda times dr? Because that's what I call the switcheroo. Because instead of integrating over dm, we're going to integrate over dr. And we're just getting dr in terms of dm right there. Once you see it once, it'll make sense. So we'll go back to our fundamental definition of moment of inertia for a continuous mass distribution. And we say, okay, integrate from 0 to m of r squared dm. But we're like, it makes a lot more sense as far as points of rotation go and things like that. So let's just get the dm out of there, and we're going to integrate over the r, because then that tells us about the point of rotation. So instead of dm right there, we're going to say dm equals your lambda times your dr. Okay? So instead of dm, we just make that substitution. And now, the cool thing about that is our 0 point, that's where our point of rotation is, to our L right there. So we're going to integrate from 0 to L. And that's a nice little integral right there from 0 to L of r squared times lambda times dr right there. Now, don't forget, in our situation right here, we said lambda is just a constant. It's just the m divided by the L, because we're saying, hey, you know what? This board, it's uniform. Lambda is just a constant. So I can put it in here, but m, that's the mass of the board, the total mass of the board. L is the total length of the board. And if those two things are constant, we can just pull it out front. So we have r squared, we pull the m over L out, and then you all can integrate that. It's r cubed over 3. R cubed over 3, evaluated from 0 to the L, the end of the board right there. And when you do that, you're going to get something like this. And then you can simplify it down. You get m cubed over 3L. You simplify that down. And the moment of inertia for this board right here is I equals ml squared over 3. And if you look up in the textbook, we have a long, thin rod with an axis of rotation through the end. Boom. It's ml squared over 3. This right as 1/3 ml squared. So we just proved that. We integrated to show that was true. The next one we're going to do, we're going to say, hey, what if we have the same situation, but instead of putting the point of rotation in the left end point or some end point, we're going to put the point of rotation, the 0 point right in the center. And you're going to see that just changes our bounds of integration, and it's kind of cool still. So go back, watch this example, but to be honest, you're not going to get it till you do a couple practices. So let's go on to example number 2. So example 2 right here, same situation, except now instead of putting the point of rotation on the left end point, we're going to say, hey, can you find the moment of inertia for a long, thin rod like this, or a uniform board, whatever you want to think about. And instead of having the point of rotation on the left end point, we're going to put our axis of rotation right through the center. And when I say point of rotation, a lot of times axis of rotation, however you want to say it, but in this case, if you want to picture, like there's an axis right here, and that's our 0 point right there. And you can see it's going to be the same process, but if that's our 0 point, then all of a sudden our bounds of integration are going to change. Same process, and you get a different answer. But all right, let's take a look. The moment of inertia, by definition, is r squared dm, the integral of that. That's where I always start, and I say it's not super helpful to integrate over mass, because when you integrate over dr, then all of a sudden the bounds of your integration tell you where your 0 point is and where you're starting from, where you're finishing, and that's super helpful. Okay, so the reason you integrate over dr is because, number one, it tells you where you've defined your 0, because, all right, our 0 point's right here, and it also tells you the bounds of integration are going to be from negative L over 2 to L over 2, so it really tells you a lot about your situation, and that's kind of neat. So we have this right here, and we say, all right, r squared dm, and then we're going to do our little switcheroo step, and we're going to say it's a uniform board thing, again, so whatever the total mass of the system is divided by the total length, that's our linear mass density, lambda. Let's use a Greek symbol lambda to represent it, so big M over L. Big M, the whole mass of the board here, divided by the total length of the board. And that's just a constant. So we're going to do our little switcheroo step. We're going to say, hey, lambda equals mass per unit length. We're just going to put the length over the other side. And we're going to say, but you know what? We're not just talking about the whole length of the board. We're going to talk about some little differential length times the linear mass function right there. Linear mass function is just a constant in this case. And so if that bothers you, and like all I'm really doing, I'm just putting a little differential here and a little differential here. And I'm saying, instead of calling it a differential length, I'm just some r, dr, okay? And so, because one year I explained it as dl, like some differential length right here, and people didn't like that because they're like, oh, well, the length L is a constant. So I'm just saying some differential r, like some little slice. We're just going to say, hey, we're just going to add up some little slice plus this slice plus this slice plus this slice. And so some differential r times the linear mass density. It's just that this lambda can change depending on the situation. Okay, so we're gonna go over here. We're gonna say, hey, dm is lambda times dr. So I just made that substitution. You can see dm is gone, and I called it lambda dr. You're like, okay. Now, unlike our last situation, we're going from 0 to L. Our 0 point is right here, right in the middle. And we want to figure out what's the moment of inertia for a rod that's spiked through the middle, and it starts at here, and it finishes right here. If this is your 0 point right here, and this holding's L, that means this is negative L over 2, and that is positive L over 2. And when you say that, it's going from negative L over 2 to positive L over 2. That must mean the 0 point comes from somewhere in the middle, right in the middle right there. So you're like, okay, that's the 0 point right there. And that's how you're taking into account that you have a different axis of rotation than in the first example. Okay? Because our 0 point was right in the middle. So we're going to say that's our 0 point. We're going from negative L over 2 to L over 2. And you get this right here, lambda is m over L. That's a constant. It comes out front. You're going to integrate r squared, which is just r cubed over 3. So we have that. It's kind of the same thing we did before. M over L is up front, r cubed over 3. That's what you get after you integrate it. The only thing that's different are our bounds of integration. Negative L over 2 to positive L over 2. That's because our axis of rotation is right down the middle of our rod this time. Then you do this. The math gets a little trickier, so just be careful. Now here's the thing. If you set this up so beautifully like this, and even a tough situation, you can get most of the points. The rest of it's just kind of algebra. So L cubed over 2. Don't forget to cube that 2. It's going to become an 8. Then minus the negative, that's going to flip to a positive. So you get something like this. And then the 3's in the bottom. You can write it like over 24. And L cubed over 24 plus L cubed over 24. That turns into 2 L cubed over 24, which is this L cubed over 12. And then we do this, we simplify it down, and you get ML squared over 12. And that should make you happy, because if you look at the book right here, ML squared over 12, they write it as 1/12 ML squared. All right, so the big thing is this. We're doing the situation, we're doing long, uniform, thin rods and things like that. When I said there's different ways to do moments of inertia, you also have some solid discs and things like that, and you have some spheres. I'm not going to focus on that a ton. I might make you do some readings just so you could do it just in case they did throw something at you, but the most common ones are point masses and long, thin rods or boards with just different endpoints. So here the 0 point was here, here the 0 point was here. Sometimes I'll put the 0 point like 1/3 of the way through the rod. You can still figure that out. So we have that, but that is a great example. Just to reiterate, general definition of moment of inertia is integral of r squared dm, and you have to integrate that over some mass right there. But I find it very, very helpful to do this little switcheroo step where we just say, hey, lambda times dr equals dm. Mass per length times differential length gives you a differential mass right there. And I will say, we're going to do an example where lambda is actually a function. And so then you can't pull it out in front of the m over L. It's part of your integral. But we're not going to do that right now. We'll do it a little bit later. Okay? Thanks for watching, and I hope you have a wonderful day.